and just to let you know what kind of pressure is put on me, just a second before I was giving a talk, Andreas told me that when he and Sylvie shared last time, the speaker ended up unconscious. So let's see what happens this time. So as I said, this talk will be another talk about synthesis, and you know, we all know what is synthesis, right? If you were here in the last decade, you have seen all this work done on the synthesis. You know that the big goal of the synthesis is like that you only specify what should have been done, what should be a program do, and not how. And then your synthesizer is supposed to automatically generate code. We have seen all sorts of flavors of synthesis. Synthesis comes when your specification is about complete, that you provide the proper specification. Let's imagine you need to give a full specification of the sorting algorithm. Your synthesis can be that you just provide a couple of examples, say like, look, those are illustrative examples that are telling me what the program should do, and then the program should generate code corresponding to these examples. This is known also under name programming by examples. We have also seen SIGIS, where you actually provide code skeleton, test harness, and then you generate code. When it comes to applications, we have seen Flashfill, I have to say, then we have seen standard applications based on the string manipulations, data functions, and so on. So in my talk, I will try to address two questions. First one already today Aus managed to answer, like what are applications outside of the usual domain, outside of the papers that we have seen previously. Okay, I'm changing my program, how can you synthesize the differences? And the next question will be, I've showed you all sorts of specifications that can be there. It can be complete specification, partial. What if there is no specification? I mean, what if you need to start one step before and actually specify, synthesize specification? So this talk will cover these two new topics coming under this umbrella of synthesis. One will be about synthesizing specifications for configuration files, and the other one will be about not programming by examples, but repair by examples, and that will be specifically focused on firewall repair. So that's two topics that I will try to cover, and let me start then with the firewall repair. And as Sylvie said, I want to also thank and acknowledge Facebook for that for award. That was actually not upcoming award, but this was award given in the networking. So it's, who would say that a couple of years back that I will be working in networking, but here I am. So when it comes to firewalls, we all know what are they, right? There are some programs that are protecting and directing how network traffic goes towards our internal home, or maybe even some university firewall. And when I ask you, did you ever wrote firewall? Probably the answer will be no, because even none of us actually ever experience or dealing with firewalls, right? We just download them and use them as they are, and if it's needed to change something, then actually we go to user forums. And that's actually how we got inspired for this work, because we were working on programming by example and then looking at the problems that usually people would pose. They would not be, I want to program something, and they would actually go up here into the area of firewalls like, I want to change something. The usually typical question was like, here is my firewall, and it should supposed to accept the following packets and drop the other type of packets. And we have seen many of such examples. So these are just some like screenshots from the various user forums that we found. And let me actually show you one example that is a little bit changed so that it fits on the slide. And that's a real example that only a bit shortened that we found on one of these forums. And you don't need to read what is happening, but you can actually see there are things like, I want to accept something, then I want to drop something. And now imagine as a user, you want to say, I want to drop everything coming from this IP address. So you actually say, written in IP tables form, you will say, everything coming from this IP address, it should be dropped. So if you look at that way, now it's pretty clear that everything coming from this IP address should be dropped, right? But it's not the case. Reason why it's not the case is the following. We need to look into a little bit about semantics of firewalls. So every firewall actually consists of the set of the rules. And this rule has some, let's talk in our language, they have some precondition which will cause which action you have to take. These actions can be either accept package or a drop package or jump to another ACL and so on. So in this particular, and so what is happening when a packet arrives, it goes through every single rule, and the first rule that it matches, it actually does what this rule is specifying. So if something is coming from this IP address, it goes through the firewall, and if it matches a rule that comes before, then it will accept. And then independently that here is the packet, here is the command, it will not happen what user you had intention. So you can say when you look at how hard is to read what this IP table is specifying, and taking into account how non-experienced we all are with the firewalls, then it's clear that user actually ask for directions and explanation how you could change one. So whenever you need to change something, what is there to rescue? It's of course synthesizer. So we started first. We first thought that we will do programming by example in the standard way. You provide some examples and you generate code. But then in this case, we are kind of almost ignoring this already existing firewall. So that's why what we introduced was repair by example. And we developed a tool called FireMason that I will now just briefly describe how it works. And the tool works as follows. It takes as an input some IP table or any other firewall, and it takes example where you say everything coming from this IP address should be dropped, and then it synthesizes code based on this already existing code, and actually it provides a new firewall that is here. So, I mean, that looks really nice because that was a very simple 4-line example that fit on the one slide. But now, of course, questions are like, what are then challenges in this approach? First challenges is like, which rule will you add? I mean, you can see that adding certain rules can actually mean that you didn't do what you actually had in mind. Similarly, now you can also remove some rules. Then what can happen? You can ask, okay, now if I remove some rule or change something, all other packages that they had in mind, will they still behave the same way as they were behaving before, or now their behavior will change drastically? So that was like, first how to decide what to add, where to add, how to make sure that, you didn't break anything, and also where then to insert new rules. So that was the questions that we have to face. And there was already, people were looking into, in our field, in the verification of firewalls. I mean, you could look into work done by Rajiv Valoor, by Sharad Malik. They were all working in that field, but what they were doing, their work was mainly based on set solving, and it was about verification. And I've seen that in next section, we will have a talk about stateful networks. So when it comes to statefulness, that means you cannot just say accept or drop. You actually also want to have some sort of memory, saying like, okay, I want to limit number of the packages I will receive from Andreas. I only want to have 7 packets per minute, and that's all I will accept from him. So you can see that it doesn't actually mean on whether when packets comes, but you also have to have some sorts of history behind it. So that's why we cannot just model anything with everything with set solvers. We actually had to step a little bit further, and we did step into SMT world. So what we did, we took a firewall, and when we translated the firewall into a set of SMT formulas. So with these things, which was, of course, we could then all heavy computation, especially if you need to deal with integers and stuff, they are given to SMT solvers, let them do lifting. And in addition, if we have a formal description, then we can also specify what does it mean that nothing else will be changed. And recently I was giving similar talk, and then people were asking me, so can you actually, which properties can you do? First, as I said, we started with verification of these firewalls. And when you think about, if you take a firewall and translate it into some big formula, then seeing that the firewall corresponds to certain, adheres to certain property, let's say that everything coming from this IP address will be dropped, is just formula entailment. Repair you will see it's again formula attainment, but running in the loop. Now soon you see running in the loop, like how many times? Well, it's fine, don't panic, because only logics we are using is linear integer arithmetic and uninterpreted functions. So scalability was not such a big an issue. Even running loop 500 times was fine. And then the one question more was like, but can you then find the rules that are pretty much useful, that are just that code? Yes, we can, because all you then have to do is find formulas which are subsumed by other formulas and just throw them out. So let me maybe briefly describe you how this SMT model will look like. Whenever you want to describe something, I won't go very deeply, I just want to give you a flavor of a couple of axioms. You have to introduce functions, you have to introduce predicates, right? Because I don't know if Andreas remember, that was my master thesis, taking one big project and then describing everything into first order logic. So, you know, everything comes back to the full circle, right? So we will use functions which will be ACL number, which will just tell me how many ACLs I have, how many ACL length will be a function which will tell me how many rules I have. Rules will be each rule enumerated within ACL. Protocol will be just enumerating protocols. Then we will have predicates which will tell that something is a valid ACL. If I, like I just don't just provide you a random number, but really in this number of the numbers that we enumerated. Then we will say reaches, which say that packet is reaches in ACL rule R. Then we will say that reaches the end, matches the criteria. So let me maybe show you one or two axioms. So this axiom says that if I have if a package A will reach rule R in A, this is ACL, and it matches its criteria, then we will also say that it's matching the rule. Now, if you look the next one, this is actually will exactly state the things that I described you before. If I will have a valid rule R, so I have one rule, and the next rule is valid, which means I have a rule, and there is a rule that comes afterwards as well. And I reach as a package this rule, and I don't match that rule. So I know that then I will just go to the next rule. You see, it's just everything that I told you how before, how do they behave, we were able to describe with simple first order logic formulas. When I say simple, that actually took a couple of months to really properly formalize that, but you know, the problem is when you're presenting formalizations, then you actually don't see all the failed attempts and all the, let's try this direction or the other direction. You just see the nicest, the cleanest version when your question is why it didn't start immediately. Well, it took some time. So anyway, to go back is like we have this, we have a firewall, and then we describe behavior of the firewall with a set of rules. All this translation is done automatically. And then once we have that, then I can address one of the challenges which was before, which is like, how can we make sure that our firewall, now that is repaired, doesn't break anything that was given before. And here is a formula. We don't need to really read the formula into details, but what does it say is the following. We will have two firewalls, firewall M and repaired firewall M prime. Now in this firewall M, if I have a package which is not covered by example, then every package in the old firewall should end up in the new firewall with exactly the same action. So this one is somewhere here where I say like terminates with the same action. Or the other possible solution is that what will happen is that, you know, like one package is covered by examples that are provided. And once that means that actually it shouldn't behave exactly as before, but it should behave as exactly as examples are stating that the new firewall should behave. So that was the rule that we could do. And then what we then do, we actually put this as an insertion into every new firewall. And then for our final, when we run the loop, that means that whatever we are changing, we at least know that we didn't break anything. So big picture of a FireMason is given here. You take me original firewall and you give me examples. Now let's just focus on the lower part. We translate this into the set of rules. And then we derive, now if you look on the upper part, we will derive, again, a new rules, which will actually be either stateless, like in this case, everything coming from this IP address should be accepted or limited, or more this rate limiting. That's what we will come next, which actually you have to have some sorts of memory behind. So anyway, you define a new rule, and then I said, I mean, what we then do, we actually run in the loop trying to find where is the best place to put it so that our assertion that you have seen before is still not broken. So that, you know, like you're satisfying all given changes, and at the same time, you don't break anything that you shouldn't be breaking. And then as an output, you provide repaired firewall. Of course, this is not only repair tool. I just kind of focus on repair because it somehow was required additional looping. We also do verification, where you can just say, verify me that everything coming from this IP address will be accepted or rejected, or some other property that you can specify. So if you have a questions, please free to ask. I'll gladly answer. So yes, please. Yeah, this is, no, the question was, does order of examples matter? And this is an excellent question, because there is something that I almost kind of try to sweep under the rug, but this is exactly a great question, because if you notice, there is one box which is called consistency checking. So when you give me example, like saying like, everything coming from your address should be accepted, and everything coming from this protocol should be rejected. And what if I have something coming from both, you know, your protocol and your IP address? Clearly, we call this, I mean, if you look officially from firewall perspective, it's pretty much clear what you should do. First rule that you match, then you actually, that this is how you behave. However, if you're a user which is just providing this example, we will warn you about that. So we called it consistency checking, but if you look what is really that's more about ambiguity checking, because, you know, like we will ask, look, this is possibility that you said that you want to accept these things and you want to reject these things. So what is the action? But I mean, from a strictly firewall looking, there is no ambiguity, but looking from a user perspective, we still provide what the question asking user what they actually want to do. But thank you for question, excellent question. So now I want to go to a part where we have seen all these things that you have seen. We could somehow model them also using set solvers, but let's go a little bit further and go and address rate limiting rules. So rate limiting rules depend on the, well, they actually specify how many packets you want to accept per minute. And they're based on something which is called token bucket algorithm, which was introduced in 2002. And to explain you, when I say that I want to get one packet every 6 minutes, 6 packets per minute, as we have here in example, that doesn't mean that I want to have a minute empty, and then I will just get 6 packets, then I can get 6 packets and a minute empty. No, the algorithm is based on the uniform arriving of the packet. So if it's 6 packets per minute, that means you are supposed to get 1 packet every 10 seconds. Now, of course, this is not very doesn't really reflect how network behaves, because if you think like sometimes you will have lots of throughput, so many packets will come, sometimes some packets will be, you know, like delayed. So the algorithm, this original token bucket algorithm also accounts for that, and they are actually having something which is called burst and a sub. So let me start. I will talk to explain you better what is happening. I will tell you about a little bit about that algorithm. I will tell you more about how rate, which is pretty understandable, 6 packets per minute, and burst, which will be 3 packets. You can imagine it as the size of the bucket, and this is actually where the name comes from. Token bucket algorithm. So we have a rate of 6 packets per minute, which we said it's 1 packet every 10 seconds. And then we have here a bucket, which is size of a burst of the size of the 3 packets. So what will happen here, let's look at the time 0, you don't have any packets, your burst is full, and at the time 5 seconds, first packet arrived. So which means you will take 1 unit out of bucket. At the time 9 seconds, second packet arrives, you take another unit out of the bucket. And at the time 10, no packets arrive, but now you actually, this is the time when you actually are expecting your packets, so you increase the size of the bucket for 1 value. Now at the time 16, there is still 2 packets arrive, there is something in the bucket, you take these 2 units out. But now if at the time 17, some packet will arrive, that means I don't have anything in the bucket, I cannot match against that, so this packet should be dropped. You see, the idea of bucket is that kind of tries to mimic this network behavior that, like it's not that everything can come in uniform way. And so what we did, we actually implemented this, we implemented also repair and verification based on this given token bucket, based on this given token bucket algorithm, where you as a user could specify that you want to, let's say, limit the number of the packets that you will arrive. For example, here I will say that I want 1 packet every 10 seconds, so by using this protocol 17, I think this is TSP protocol. So which means that how we specify, we'll say, okay, start with some point, there you should accept something, in the 10 seconds you should also accept something, but everything in between should be dropped. So like we kind of indicate this, accept everything 1/10 seconds. And let's assume that our given algorithm is our given firewall is very simple. It's 1 single script. When we synthesize the repair, then it actually will see that will be exactly what we said. I will have a limit of 6 packets per minute, which is 1 every 10 seconds. My burst in this case, because I didn't provide anything, will be pretty small. It will be just burst of 1, and everything that coming will be, it should be accepted. And I also have to indicate the other rule that says that everything else should be dropped. So when it comes to modeling, in the paper that will appear in the proceedings, I put the links to existing papers and also the links to the GitHub page. If you would like to see how we model that and see all the formulas, you can look there. I won't go again into all the formulas because that can easily fill the couple of hours and just hardcore mathematical symbols. But it's interesting to see is that how do we model here? Of course, this was unavoidable without going into linear integer arithmetic. So we would have a formula which would try to capture how many packets you have received until now, how many packets are still, were until the next measuring time, and all sorts of variables like that. So, and that's some of, if you will want to look at the formula, those are important to remember. Like when it's TP is arrival of the packet, how many tokens you have before this packet arrive, how many they will be after, and so that's this way we could manage to model time. And I'm looking forward to see next talk, which I didn't see, to see how do they model statefulness, because this is not only stateful problems to address. I mean, there are various other things that you see in firewalls. For example, especially when it comes to authentication, you want to say, well, I will communicate with you only after I receive authentication tokens from you. So that's other things that we have to measure. So to go to the a little bit about running times, you can see that with all these 5 examples that are there, all of them are user-inspired examples. Each of them has their own Stack Overflow, super user, or any other page. We took exactly firewalls provided by user and exactly examples provided by users, and we tried to go and fix them. And you can see in the running times, I mean, they are in milliseconds, so it's nothing scary, because even the one which was with rate limiting and authentication protocols, it took us, and I think it was over 500 rules, it took us less than 3 minutes. So, and this is the one that scares like the biggest one. So then, of course, we were using all other things because, you know, when you're trying to, when you're trying to show that these things will scale, we would generate our own firewalls, because it's really hard to access some company firewall or I mean, the only thing we could really play that is a real firewall was that our system administrator gave us to peek into into firewall of our internal lab. So that's what we could play with. But so we generated our own rules, tried to see how it will scale, and you know, like you can see that it scales like if you have over 500 rules, it's still pretty much around 3 minutes or so. It doesn't really go, you know, like you would expect if you're using arithmetic that it will go, that you will somehow get into exponential mode, but it's kind of keeps this exponential under the control. And to summarize about that part of the talk where I showed you that you know you can do repair by example, not only about programming by example, this FireMason was a first tool that we are aware of that can actually repair firewalls and including this limiting. And as I said, we were really proud that it was evaluated on real world examples. It would be nicer if we could capture some real firewalls of some company, but that's, I'm pretty sure, not going to happen. I mean, my postdoc is right now working at Alibaba, so maybe he's working on the real world, but I'm pretty sure either he or I cannot tell you about it, that would be legal. And if you want to play with it or check it for yourself, it's available here at the GitHub webpage of Bill Hallahan, who is my student. So I don't know if I said at the beginning, that was done with my student Bill Hallahan and a postdoc Enan, who is right now doing, who is right now at Alibaba doing as a senior research scientist, something like that. So if you know all about firewalls, so are you ready to hear more about how to synthesize specifications so that we can do synthesis and verification? Okay, so let me then go to the next topic. So this work was again with my student and postdoc, Mark Santolucito, and this was about verification of configuration files. Remember, I told you that I will show you 2 new topics that you will rarely see in typical conferences that we are attending. So I think this was one of the first works that we actually published 2 years back at CAV, and now I've seen that there are so many works that are also again done on configuration files, so that's really nice that we kind of managed to discover a couple of months before the other said this is the problem. And our secret source was that we had a person from systems community telling us work on that. And to tell you a little bit more how we actually inspired this, he showed us this work that was published in SOSP. And you could take a big servers, and they were searching for what was the cause of the downtime of these big data centers. And it turns out far biggest problem was in setting up wrongly configuration files, 31%. I mean, see, we are all working in 15%, well, we should actually also have a look into 31% direction. So when we started to look into configuration files, they usually look as follows. I mean, that's a bunch of very unreadable code that no one besides a couple of people who wrote them understand what is written. And this here that you can see is PHP initialization with Apache and MySQL. And imagine what can happen here if you would just this is again a real world example. What has happened here was that this just was reporting segmentation fault. And if you imagine that you change only this part, and so because now it's okay, maybe if I look closer to this part, I can see what is the error. And looking here at the error, maybe some of you know, but the problem here was, it was actually linkage error. Problem was that you actually had to load the recode library before the other library. I mean, it doesn't matter that you loaded them both. One has to come before the other, otherwise you have a linkage error. So it won't work, like, let me just take existing file and add the library that I need. You really sometimes have to respect this ordering. And if you would call on the all file, our tool which we started, we had the sequence of the tool. This one was first one, which was called config-c. But this tool will tell you, look, what is the problem here is that this recode was actually appearing before MySQL. That's wrong. Our tool analyzes the whole file and immediately reports that that could be an error. So let me show you another example, another configuration file looking as the following, and let's assume that this one simply failed to start. And let's assume you actually only change the following line. And if I ask you, what is the problem here? Those who know, please. No, those who have seen this talk, don't answer. So what do you think is the problem here? This file, when you set it up, and it just failed to start.
The directory does not exist?
The directory exist file is there, you have all the writing things. So the problem is that that was Boolean. So you will say, look, general log is actually just a Boolean, which will tell that you will use general log file. And you cannot just say general log is this, you actually first have to say that you will use it, and then you provide the file name. And our tool will tell you, we already have probability. I will explain you where the probability comes from, saying like, look, I'm pretty certain that this actually has to be integer or Booleans here. So now you have seen a little bit of configuration files, you can actually see what is the main problem. I mean, the main problem is if you want to verify them, or even we try to synthesize or repair, first specification is missing. Then, of course, you will say, okay, if there is no specification, let's write some specification. But writing the specification will be pretty labor intensive. And if you're writing specification for something like this, it's kind of practically bound that you will have to make an error. Then the next thing is like, you don't really get errors. I mean, you will get segmentation fall or things didn't start. And this is actually the best case, because when you have error and things are not working, then you know that this is great, because when you repair and things are working, then you know that you actually fixed your error. There is another serious problem here, is the following. If you set up some parameters wrongly, it will work, but it will work practically like a denial of service attack. I can tell you from my own experience, embarrassingly enough, I was already working on configuration files. We were running this student competition, IC student competition. And we had it online, so which means actually you come there, you log in, you set up your data and stuff, and first half an hour, everything goes perfectly. Like students get there, they set their logins, they start to send data, and suddenly after half an hour, everything was wrong. You couldn't log in anymore. You couldn't submit your solution. Nothing was working. We check connection is perfect. We check everything. And, everything was supposed to be working. You know what was the problem? As I said, configuration files, we didn't open enough of ports and sockets to log in. So, this is a type of error, okay, that our tool wouldn't detect, but this is a typical errors that, could happen, that maybe you will allocate not enough memory than you need. So this is a typical example. Another here is that what that can happen is like you will have, let's say, you have multi-threaded programs, and to each thread you give some buffer, and then you say my number of threads will be 7, and each buffer has, I don't know, 5 megabytes or whatever. And then, but the amount of memory that you allocate is maybe too small. So which means that although you have super powerful machine, your resources that you allocated are not good enough, so you have constantly competition for resource, and everything is just slow. And in this case, it is working, but it's just super slow. So, there are such errors that are really hard to detect. Anyway, so I don't need to tell you, the documentation is practically non-existing, and that only way of repairing something is hoping that someone else had the problem and reported to that problem before, and that you will be able to fix it. So what we did is we said okay, let us then go, as I said, this one step before, and let's actually generate specification. Because once we have specification in any form, well, that's better than nothing. Clearly, this specification won't be complete, but at least it's something. And then we can actually check our existing configuration files, whether they actually correspond to this given specification. So this is actually very high-level picture of what we will do. I mean, we would take a large number of existing configuration files, we will learn some rules, and once we have rules, we will call that specification. Now, if you look a little bit closer how this will actually look, I will now explain you a little closer this problem of learning rules. So the first problem is that how could you even learn rules, right? They are not typed. There is nothing that we could actually start to, get hands on things that we already are aware of. I mean, so what we then did, we said, okay, we can learn if all these variables would have certain types, then it would be easier, because then we could introduce standard templates saying, let's say, whenever I'm talking about integers, I can compare two integers, I can multiply them and then compare this. So, like this would be nice. So if we would have this predicate database, which would be type-based, then we could actually learn something, because whenever you would learn that, let's say, variable, what was it, like a general file, if you learn this variable is always Boolean, and the other general file log is always a file name, then you could actually check, say, like whenever I'm talking about file, I want to check whether the file exists. Whenever I'm talking about Booleans, I want to check whether two Booleans are connected. So things like this we could learn. So which means that now we have to take these existing files, and we have to actually translate them somehow in intermediate representation, which will kind of give us this power of at least using some sorts of typing. So we will introduce, we will translate configuration, all the variables that appear there, we will also assign them with the types. And then we will use existing database, and for that we will learn rules. Now, when it comes to learning rules, that's like really nice, like all this big picture, but how can you actually learn rules? And for the help, we actually get something from databases. So in 93, Agrawal introduced something as called association rule learning. So association rule learning is the thing which tells you, okay, when I'm looking to big databases, I want to see things which are always kind of coming together and which are always connected. So you can see we are going somewhere in that direction, right? For example, if you do shopping, if you're buying bread and peanut butter, most likely you will also put jelly in that shopping list. Example that you see below is also that comes from same paper or same tutorial, and I have really no clue how beer and diapers are related, but apparently if you're buying one of them, you might buy the other. So what we tried to do then was actually use this learning that Agrawal was using, which was, like see which things are related, and instead of learning, instead of learning what is purchased together, we actually wanted to learn things like which are coming together in the things which are coming together in the ordering, or things which are usually compared as the variables. So we would learn such stuff. Now let me tell you, I will tell you a little bit more also later what things we needed from this association rule learning. But let me start now tell you a little bit more about predicates. So predicates that we consider will be all typed, so we will consider that two things can always be ordered. If we have a keyword, then we will actually check whether two keywords are coming together in the same file, because very often the case will be if you're loading one library, you also have to load the other. Maybe it's not related in which order, but like when you use one thing, you definitely need to use the other. Typing will be a special issue, because when it comes to Booleans, there is approximately, I think, 12 or so cases how that something can be set as a Boolean. It can be one, it can be true, it can be enable, it can be on. And let me continue. Okay, I came only to 4, but believe me, there are a bunch of them. Then if you will have two things independently of which type, you can actually compare them. When you have integers, you can also compare integers, but we will also consider more fine-grained things, like when you have couple of integers or sizes, you actually have to see whether they are actually satisfying some relationship with multiplication. And this is exactly needed when it comes to working with a couple of multi-threads, with couple of threads and their buffers. That was typical examples while we have to also introduce this type of predicates. So predicates were all inspired, again, by talking with people in the system research and also looking at the user problems to see what kind of problems usually arise when we are playing with data, with configuration files. They even, in this paper that I mentioned from 2001, they have one really large table that they can classify them in 12 or so classes, and I think we can cover all of them that are not really coming from outside, like, you know, when, for example, network is not available or so on. So now let me go a little bit to probabilistic typing, right? You can, what we want to learn is when something is a Boolean, when we want to learn what type some variable has. Because from when you see something, let's say foo, if I would just give you foo here, you will see that foo is on, so most likely is a Boolean. But if you look bar is 1. 1 could be Boolean, but 1 could also be an integer. In the worst case, it could also be string. Or if you call your file one, that's also possible. So, right, that's possible. But then if you look in the next section, then I'm calling foo again on, and bar is on. So bar is now most likely Boolean as well. So from when I analyze, you can see where I'm heading. The idea is you will analyze a large number of files. So what we do, let me kind of focus better. What we do is the following. I take a variable, and I go through all files. I see through the files whether this variable is integer, whether it's Boolean, and I collect all possible values that it can have, type values. I will say now, right now I suspect that bar is an integer or string or Boolean. In the next one I will say, I see now that bar is only Boolean. So what we will do, we will collect with every single file variable, we will collect, well, variable is not the right word, it's more like keyword appearing in configuration files. We will correct all possible values that it can have, and then we will provide a list of rules which will kind of determine which is actually its type. So you can actually think about, they're more like, my student like to call that quantum types. So initially, variable can be everything or anything. You connect all the values that it can have, and then at the end, when you actually satisfy some of the given rules that we have there, for example, what we are saying here, that if something is of tau tilde is one of this liquid type or probabilistic type, and then if it satisfies whatever rule we have on integer rule on the liquid types, then I know that this is integer. So for example, we will say, if I see that something is in 90%, if I look at the size of the vector and everything that it can be, and in 95% it was Boolean, then I'm pretty sure it was Boolean. That's a typical example, a typical predicate that we would consider. So at the end, right, we don't have types, but we learn which type of each keyword should be. And once we have that, then we can actually apply all these rules that we were using with the template, saying like if I have two values of the same type, then I know I can compare whether they're equal. Because in this particular case, you would have foo and bar, which can be either on and or, 1 and 2, but yet I will actually be able to see that as I suspected that as a bar was once only integer, 3 times Boolean, and foo was 0 times integer and 3 times Boolean, so I can conclude that bar is Boolean and foo is also Boolean, and then I can actually see that they are actually equal. Although if you would do this pretty on semantical level, 1 is not equal to on. You see? But I could actually, by doing this probabilistic learning, I could learn these things like this. So now let me go back about learning. One thing that was very nice, you can see how we actually, rules were pretty much learned the following way. First do this typing, infer types, look at the types of the predicates, instantiate all the values, and see which things could be true. So for example, let's say I will see that A is smaller than B in one file. Then I will see in the next file that also A is smaller than B. But then in this part will tell me that A is smaller than B. And you will just tell me that B is the other way. So is this the rule or not? Now that's the question, right? Because what I didn't tell you is that how can we actually have access to very large number of existing data? Well, if you have really large number of the data, that data is most likely noisy. And you cannot have guarantees that everything is correct. But using the wisdom of the crowd, you can say, well, it's not that every single person will do error in exactly same place. So probably errors will, be not very often. I mean, they will occur, that goes without saying, but you know, like they won't occur very often. And for this, again, comes help for Agrawal, which actually it gave us a proper formulas. You don't really, I mean, if you want, we can read, and I even have some examples, but what I want to say is what these formulas are telling us. They're telling us when you learn certain rule, let's say you all claim that A is smaller than B, and I have seen here that B is smaller than A. You want to actually have a confidence. So here is the rule for the confidence, which says like how often this rule is actually true in the set. You know, like, if it was true in more than 95%, then let's go. That's most likely correct rule. Probably this one was noise in the data set. And that's why, if you now remember, when I showed you the output of our rule, of our tool, which said, like, look, with probability 1.0, I'm sure that this has to be a file. That's why actually this probability comes, because when we report to user that there is some error, we always say with probability 96, I'm claiming that these values should be maybe differently ordered, or you know, like this is where probabilities are coming from. And then support was the thing that was really helpful to us, so that we actually managed to get rid of many false positive. So support requires that when you look at the sample as whole, you actually want to also have some confidence that this is the rule. That not only that you have seen it, you know, like once or twice, you want to see it at least in certain number of percentage, so that it's not, you know, like some just, you know, like accidentally it happened that A was smaller than B, no one else contradicted it, so it must be the rule. And then you actually use this as a rule, while, you know, like when you actually get all sorts of false positives. And in this sense, you know, like you don't really want to get too many false positives, because no one else will then check and use the rules. So here are some examples how can you actually compute support and confidence, but I guess this is just, you know, like again, it boils down to counting and dividing and finding the numbers of this. But I want to actually give you more the numbers that we set off. So when we started this project, we didn't have configuration files to start with, but we have a system guy. So what we ask our system guy is like, can you please take these 25 configuration files and make sure that they're all correct? So okay, we started with the 25 or 50 configuration files. They were all correct. So in this case, we really had confidence of 100%, well, modulo his correctness, that every rule that we learned was actually, every rule was actually correct, and we really didn't need to put any barrier for a threshold, because whatever we learned, and since nothing was contradicting, that was correct rule. However, what has then happened was, of course, we were immediately from the day one aware that this is too much human in the loop, and that, you know, that definitely will not scale to the large number. But again, what is very nice is that system community, they were actually collecting all the broken configurations. So you have this very large couple of gigabytes existing set of misconfigurations. So we know that they're mostly broken, but we don't know really where they're broken. So what we said, like, okay, that's perfect, then we can learn rules, but that's why we actually had to switch from we know that everything is correct, to the association rule learning. And then we actually had this threshold. They said, like, I want to approximately that rule appears approximately 95% correct, then I will consider it a rule. And it's also, it should be at least 10% visible. That it's not that only, okay, I learned once that A is smaller than B, and I would claim that this is a rule. So now when it comes to checking, again, if you will want to see all the standard evaluations that you have to do for the paper, right? Like, how does it scale, how fast it is, how all this is in the original papers, they're there. But what I actually want to show you is somehow way more interesting to see. What has happened was, when we submitted this paper, one of our reviewers, so even if someone is sitting here, said, like, you know, like, this is all nice, but why you don't actually send your feedback to real users? And the person I said, like, run your tool on GitHub. Ask people what they think, whether you contacted the real whether you found actually the real errors in configuration files. And we're like, oh, wow. Like, first, of course, reaction was like, what the reviewers know. But then after that was like, that's actually a pretty smart idea. Let us try. So then we actually ran it on GitHub on the existing this configuration files. And I actually picked up some reports. So that's what users were saying. And one thing that was, you will see on the next slides also some reports. First, like you sent around 1,000 or so, like a confirmation to GitHub, like, hey, we developed this tool, we found an error in your configuration file, can you confirm whether this is a real error? Imagine if you're there and someone sends you this message, there is really big chance you'll just like, who cares, ignore. But nevertheless, people did answer. So I put here answers from real users. And what was very often the case, and that's why we were proud, was the following. People will say, well, you did found an error, but if you look a couple of iterations later, this was exactly the error that we detected as well, and we actually changed this. So like, thank you for pointing out, but this was actually found, and we found it and changed it. That was on the cup. That was often that appeared, and all the feedback that we received, but one, were very positive. But one person, this is taped, right? One person was very negative, and your client really didn't like what we reported as an error. However, when I asked guys, and if you look, I think the guys who actually give in was exactly the person who say, wow, thanks guys. So that was exactly the same error in their both files. So later on, I asked our system guy again to check whether this is, like you can't get to such a different comments, to check whether this was indeed an error. And our system guy said like, yeah, this is indeed an error. And then he explained with the very long things when actually just spent nodding and, okay, if he says it is, I really cannot repeat why was this even an error? But apparently it was. But I think actually it was really great idea to, like to take your tool, send it to the real users, and not knowing what you will get out. It's not, like that you ask 5 PhD students from different lab and they give you nice feedback, but this was really like, let's see what will happen. And I thought that we were happy with, of course, we were a bit shocked when we got it, but not happy with when we got your client, but everyone else was fine. But to conclude now, this part is right, again, everything is available online. We automatically infer here a specification from existing configuration files. Once we have a given specification, we can use it for everything from verification. And what we were really happy was that we were really happy with the false low positive rate. So one thing is, again, as always, that when you do something that is like borderline system, which is pretty systemy, is that you want to see whether this will be applied in the real world. So Raul, who was one of our collaborators, he was working in MongoDB, and he apparently worked on exactly this for distributed databases. But as everything time is with the industry, he didn't publish anything, and he cannot tell us more except that this was somewhere applied. So what we have right now going on, that was published by my student at ISDA last year, and we kind of extended this to go further, is that we applied this to Travis CI rules. So I cannot tell you more, but this is a pretty cool thing, that because we actually don't really have only, like configuration files, but you also know whether the configuration failed or succeed. So we more or less pretty much know which configuration is correct and which one is not. So we are now learning rules from this part, and then the next direction from this is like, because I'm at Yale, there is this big group of gens who are working pretty much on the low-level kernel. They want to apply this to, we were talking, want to see whether we can find errors in installation scripts. So now to conclude all this, what I told these new forms of the synthesis, you have seen starting today with our paper that synthesis is actually couple of steps, like you could never, like couple of years back when you have seen the first paper about synthesis, would you ever confirm that they will be applied to the reasoning that something is fair? Now, we've also wanted to show you that, like it could also go towards system community. I mean, verification of firewalls, configuration files, previously those were really more system community topics. One thing that we learn in this is that first, of course, you won't have specification, you won't have things that we kind of assume should be there and they should come for us for free, that you can nicely work with existing things. All these things you will have to do yourself. And then what is very hard, and it's find a suitable model. As I said during my talk, one thing that is kind of, when you see the result, it looks like exactly this is what you should be doing, but there is lots of attempts of like, maybe we should use this model, maybe we should use some other model. So, like those things you cannot quantify over. And what is really nice that we both tested them on the real world examples, and if you would like to play with any of them, they're available, and I'm now happy to take your questions. Thank you. Should I hold that I don't faint? Please.
Very cool work. Yeah. Very cool work. With regards to configuration, so it seems like the problem of discovering rules can be applied more generally, not only to configuration files. I mean, as you suggest, Linux installation file, but even like maybe API usage. Have you thought about things like that? And my other question, it seems like with configuration files, the problem is like a more higher level in the sense that it's just a language design problem.
Oh yes, I mean,
that is totally nicer abstractions to do configurations might,
Oh, I very much agree that this is language design problem. But with when it comes to that, I mean, there were a couple of attempts in system community. I think it was from Microsoft Research where they actually tried to develop a new beautiful language for configuration files, but there is huge legacy code. Like it's. No one wants to learn new things when you actually have this existing configuration file, add 5 extra lines, and let it run, right? That's the problem. So I very much agree with you that it's just poorly designed and it looks horrible and unreadable. Same like firewalls, it shouldn't look like that. But what can you do, right? It's there, it's legacy. So it's more like helping legacy code to come to verification. But excuse me, what was your first question? I will repeat. No, we didn't look into it, but I agree. I mean, last year we had a faculty candidate who was very excited about that, and she was considering actually similarly into your direction. So maybe you know her, Hima. She's working in detecting. So she's working in detecting cases, rules for the court cases. She was at Stanford, and she thought that it would be really nice if we could extend it. So maybe we should actually talk after in the break. Yeah.
For the rules that you learn, these configuration files are also read by some C program or some computer program, right? That reads them and gives the errors. Did you ever think to analyze that program and see that the rules that you learn are consistent with like ideally you would expect that you can read the program source and you can get the rules from there, not from
I mean, there is also. Actually, that was a paper. Excuse me, name is escaping me. Looking into C programs and then analyzing how the program is written and see what will actually invoke, like break and stuff and ruling this. That was work done. It was published, I think, at OSDI or Apple's a year or two back. So it was this. It was there was work into that direction and. I really I cannot remember name. I know the guy was Chinese, and I have to look into his. I mean, my postdoc is Chinese, so I'm and my very good friend. So I should be more remember the names. But if you ask me like this, I really cannot remember name. I'm sorry. But I know where to look. I will tell you immediately after. Where is it?
Thanks.
Sorry about that, yeah. Please.
Many configuration files are wrong, and many are copy-pasted from former configuration
Yes.
files that were wrong with small changes.
Yeah.
And also there are some configuration files for linking and things like that that
Yeah.
have absolute address and things like
Yeah.
that. And so in your rules, you might end up with a big or of all possibilities. And how do you avoid that? And the second one is, how do you make sure that the rule you learn are correct, since you don't check the learning set?
So let me first answer how do we check the rules that we learn. So exactly for the reason that you describe, we don't have correct data set unless we somehow manage to ensure that we have, which won't scale. So what we then report to user is not only the rule, but we also report the percentage how many times this rule was correct. So that means if I tell you, let's say, you set up A to be 700, and everyone is else setting up, to it's 70 and not more than 70. I will tell you 98% this is different. So that when I report you this number, then you as a user, because we don't really do automatic changes, we just report to user which errors do we believe are there in the file, and also with our confidence. So that's why in the first or second example that I saw, look, I'm 1% confident, but that really rarely happens because exactly for the fact that they are not correct, right? So we report errors in the sense with the confidence to see how confident we are. And then if we also put a threshold, if I think for sometimes our threshold is a bit lower, like around 80%, but we still report because then, but for some rules we have really high, around 96. But I don't think we ever go below 80. And I think we have, we have clearly rules with 100% confidence. So that's really, we always give a user confidence how we are. But how to avoid that we don't get very big ORs and unread. Actually, we don't get OR rules because we have, our templates don't exclude that. We get, like, if rules of the type, if this and this holds, then the following. So it's pretty much depend how you set up your templates. Yeah. Yeah, maybe can I just now remember one thing that I didn't. And another thing is that is not templated like ordering, because you cannot really template ordering properly. I mean, you can, but then you will get really large. So what we do when we do ordering, we are actually building, if we get indication that two things could be in the ordering relation, that's, then we actually start to be total ordering, and then it is not really templated, but it's just we're just building an ordering and then see whether we can collapse it or not. Thank you.